Hello everyone. So today I am going to present the topic conservative nature of electric field. This is in continuation to the last 5 to 6 lectures. So the plan of my talk in this present lecture are introduction, conservative field, non-conservative field, line integral of electrostatic field. Then after we will discuss the conservative nature of electrostatic field. Next, electrostatic field is an irrotational field. Lastly, we will see the discussion of electric field is equal to the negative gradient of potential. This is the plan of my talks. Okay. So what is meant by conservative field, sir? Conservative field is nothing but a vector field for which the line integral depends only on the endpoints but not on the path followed is called as conservative field. So you studied in the first year, first semester mechanics about this vector field, scalar field, vector field, the gradient, divergence, curl, all these things we discussed there, sir. If vector field is said to be the conservative field such that if the line integral of that vector field depends only on the initial and the final points of the particle followed, but not on the path followed, or it is independent of the actual path followed, is called as conservative field. Okay. So there are some characteristics for the conservative field. The first one is the line integral of a conservative field over a closed path is 0. It is very, very important, sir. Closed integral a bar dot dl bar equals to 0. This is a basic property. For any conservative field, here if a bar is a conservative field, conservative vector, field vector, then the closed integral a bar dot dl bar, that is the line integral over a closed path. The line integral along a closed path must be equals to 0. This is the the condition compulsory should be obeyed, sir. Okay, this is one characteristic. The second characteristic is a conservative field can be expressed as the gradient of a scalar field. Suppose if A bar is the conservative field vector, then A bar can be written as the gradient of a scalar potential, where phi is the scalar potential. I think you know what is gradient of the scalar potential. Phi is the scalar potential, then grad phi is the vector, sir. The grad phi is nothing but what? The gradient of the scalar potential is nothing but what? So gradient is nothing but it is the rate in which direction the change of rate will be maximum. The change of rate of this scalar potential will be maximum is called as the vector field. Grad phi is a vector. Del phi. So what is del here? Del bar is the operator, you know, I dou by dou x plus j dou by dou y plus k dou by dou z. Then when you operate the del operator on the scalar potential, del phi can be written as I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. Okay. So what I am saying here is, if A bar is a vector field, that is a conservative field, then that can be expressed as the gradient of some scalar potential function. Here we talk about the electrostatic field. Electric field is a vector field. Gravitational field is a vector field. Magnetic field is a vector field. Okay. So electric field strength also can be expressed as the gradient of some scalar potential. So that is the negative gradient of electric potential. E bar equal to minus the gradient of electric potential. Okay, so that condition is obeyed in the case of electrostatic field, sir. The third characteristic is the curl of a non-conservative field must be equal to 0. Because since the conservative field can be written as grad phi, then you consider the curl A bar, sir. Then curl A bar equal to what? Del bar cross A bar. Okay, then del bar cross, but A bar equal you substitute del bar phi, curl of grad phi. Curl of grad phi equal to 0. It is very, very important question in the first semester in the problems. Curl grad phi equal to 0. Okay. You can calculate this one. Del phi equal to, already I explained, I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. Then del bar plus del phi equal to, simply you can solve this one by taking the determinant method. I j k dou by dou x dou by dou y dou by dou z dou phi by dou x dou phi by dou y dou phi by dou z. So on simplification you will get del bar plus del phi equal to 0. So what I am saying is curl of grad phi equal to 0, sir. If phi is the scalar potential function, then del phi is the vector. So del is operated again on the vector. So the curl of grad phi equal to 0. So now coming to the conclusion. So there are three fundamental properties. Okay. There are three fundamental properties. The first one, a vector field is said to be the conservative field when the line integral of that vector field depends only on the endpoints and independent of the actual path followed. This is the first characteristic. Second, the line integral over a closed path must be equal to 0. Mathematically, we write it as closed integral a bar dot dl bar equal to 0. Okay. The third one is any conservative field can be written as a gradient of some scalar potential function. Here, phi is the scalar potential. The curl of any conservative field must be equal to 0. Therefore, curl A bar equal to del bar cross A bar, that equal curl grad phi equal to 0. Okay. Now, so what about non-conservative field? So the property is opposite, sir. A vector field is said to be non-conservative field only when the line integral depends upon the path. The line integral depends upon the path is called non-conservative field. If the line integral doesn't depend upon the path, that is called conservative field. So that depends on only the endpoints, initial and the final points. So what path you followed, it doesn't matter there. Here the vector field must be dependent. So line integral of the vector field compulsory depends upon the path. Example for non-conservative forces are frictional forces, viscous forces, or non-conservative forces. Conservative forces, example, electric force, electrostatic force, magnetostatic force, gravitational forces. Okay. Now, the second property. The line integral of a non-conservative field over a closed path is not equal to 0. Here, closed integral a bar dot dl bar not equal to 0. The third one, for a non-conservative field a bar, curl A bar not equal to 0. So it is a rotational vector. The curl equal to 0, then that vector is said to be irrotational vector, sir. Curl is nothing but rotation. If curl A bar equal to 0, then A bar is said to be irrotational. For non-conservative field, curl A bar not equal to 0. Therefore, it is rotational vector field. Okay. Here, example for non-conservative field is magnetic field due to the moving charge. The magnetic field forming due to the moving charge is the non-conservative field. Okay. Now, so what is the line integral of electrostatic field? What is its physical meaning? Simply you can understand, you observe the figure here. So this is some electric field, sir. Anyone can say whether it is a uniform or non-uniform electric field. Response, sir. So the figure shown is uniform or non-uniform electric field. By means of the orientation of electric lines of force, you can say the nature of electric field. Here the electric lines are the curved lines and the spacing between the lines is not same. Here magnitude is changing and the direction is changing. Okay, therefore it is a non-uniform electric field. Yes, so this is the non-uniform electric field. Here the charge is moving from this point to this point along some the curved path. Okay, at this point, so on this electric line of force, the tangent line drawn at that point shows the direction of electric field strength E bar. So therefore, at this point, the force acting on this test charge Q naught will be F is equal to QE. Okay, when the charge Q placed in the uniform in the electric field E, that will experience the force F is equal to QE. So here the test charge Q naught will experience the force Q naught E in which direction? Along the direction of electric field strength. What is the direction of electric field strength here? Along the direction of tangent line. So on this curved line, the direction of E bar is along the tangent line. Therefore, the force acting on the test charge is also along the direction of this tangent line. So here it is denoted Q naught E bar. Of course, this the path is divided into the small infinitesimal length elements. At this point, I have taken a small length element dl. So the direction of dl bar is like this. So the dl bar direction is this one. This is the force acting on the test charge Q naught E bar. Okay. So keep this concept in your mind, sir. Let us extend our concept for line integral of electrostatic field. Right. The same diagram I consider here. Here the test charge is moved from the point A to B, right, through some a curved path. So you consider a point P. There the direction of small length element is dl bar in this direction. The direction of electric field strength at that point is along the tangent line direction. Here it is E bar. Okay. So there is angle between some E bar and dl bar, of course. Here the test charge can experience the force how much? F bar equal to Q naught into E bar. Okay. So what I am saying, the path is divided into small infinitesimal length elements. You consider a small length element dl bar at the point P. The direction of dl bar is shown here. The direction of electric field strength at that point is along the tangent line direction. Okay, that is E bar direction. Then the force acting on this test charge or the force experienced by this test charge F bar equal to Q naught into E bar. So that force will be along this direction, along the direction of E bar, sir. Right? So this concept we keep in your mind, right? Then the small test charge experiencing the force how much, sir? F bar equal to Q naught into E bar. Say equation 1. Now, the work done by the field when the test charge is moves through a small vector distance dl bar is given by d double equal F bar dot dl bar. Okay. Work done formula F bar dot displacement vector. Here dl bar, the particle is nothing but the test charge Q naught is getting the displacement dl bar. Okay, the displacement of that test charge how much? Dl bar, right? Then the work done equal to F bar dot displacement how much? Dl bar. But F bar equal what we have? Q naught into E bar. So that is substituted here. Q naught E bar dot dl bar. Okay, followed, sir. So here we consider the small area element dl. So at that element say the point something A dash and B dash. So in moving the test charge Q naught from the point A dash to B dash, so it is getting the displacement dl bar. So dl bar displacement direction is this one. Okay. So here the work done by this field in getting this small displacement dl bar we are writing that is d double equal to force vector dot displacement vector. Force is Q naught E bar dot dl bar, equation 2. But the total work done when the test charge moves from point A to B. For the small displacement dl bar, the work done is dw. Actually, the test charge is moving from point A to B. From point A to B, the total work done we have to calculate. So therefore, we have to integrate the dw. So integral of dw over the limits A to B. So integral A to B, dw equal what we have? F bar dot dl bar. F bar dot dl bar equal what we have written? Q naught E bar dot dl bar. Right? So here write Q naught outside of the integral. Integral A to B E bar dot dl bar. This is equation 3. So from this equation, you write W by Q naught, sir. Q naught bring left side. W by Q naught equal to right side, you will have integral A to B A bar dot dl bar. Integral A to B A bar dot dl bar. Okay. W by Q naught is nothing but what? This is the work done in bringing the unit positive charge from A to B. Actually, we moved. Actually, the test charge Q naught is moved from point A to B. So then the work done divided by the charge. That is the work done in moving the unit charge from point A to B. That represents the integral A to B A bar dot dl bar. Integral A to B E bar dot dl bar physical meaning is that the work done in moving the unit positive charge from the point A to B in the electric field of strength capital E bar. So along that curved line, so whatever the path we followed along the bound, along that curved line, so we are integrating. What we are integrating? We are integrating the electric field. So integral A to B E bar dot dl bar gives that. So this is the work done in moving the unit positive charge from A to B. So that is the physical meaning of that. The line integral. The line integral over the point A to B. So the line integral over that curved line. So from point A to B, that meaning is that this is the work done in moving the unit positive charge from the point A to B. Okay, sir. So this is the line integral of electrostatic field, right? Now, so what is the conservative nature of electric field? In general, we explained about what is conservative field, what is non-conservative field. So here I am insisting that electrostatic field is the conservative field. So we have to prove that. So what are the characteristics of electrostatic field, conservative field? If the vector field is conservative field, then the line integral of that vector field along any line, any straight line or curved line, whatever it is, along a line should be should depend upon initial and the final position or endpoints, but not the path followed. It is independent of the path. This is the characteristic one. What is the second property? The line integral of that vector field over a closed path, A to B, again B to A, coming back. A to B, you follow one path, B to A, some other path. Then the line integral of that vector field along the closed path must be equal to 0. Closed integral A bar dot dl bar must be equal to 0. The third property is the curl of that vector field del bar cross A bar equal to 0. So in this, if these conditions are satisfied, if one condition is satisfied, automatically remaining two conditions will be satisfied. So by using these three properties, we will prove the electrostatic field is conservative field. Let us check that one, sir. So either electrostatic field is conservative field or not. So consider a unit positive charge is moving from point A to B here along the path via ACB. Again, it is coming back through the path BDA. So here unit positive charge is moved from A to B via the path ACB. Again, it is coming back through the path BDA. So it is completed one cycle. Okay. So here the unit positive charge is moved through the closed loop. So it is moving, it is covering one closed loop. So then we have to calculate. If the total work done in moving this over a closed path equal to 0, then we will say that electric field or electrostatic field is the conservative field. That is the approach we are proceeding, sir. So say W1 is the work done in moving the unit positive charge from A to B, and W2 is the work done in moving the unit positive charge B to A via the path BDA. Okay, so that is written here. The work done W1 equal integral A to B E bar dot dr bar. This is the equation 1. Already I explained in the previous slide that integral A to B A bar dot d bar means what? This is the work done in moving the unit positive charge from A to B. Okay, the work done in moving the unit positive charge from A to B, we represent mathematically as integral A to B E bar dot dr bar. Clear? So this is W1. Now the work done in moving the point B to A through the path BDA can be written as integral B to A E bar dot dr bar. So by exchanging the limits, by interchanging the limits, you can write minus integral a to b e bar dot dr bar. This is equation 2. Right, sir? Therefore, the total work done in moving the unit positive charge from A to B, again B to A. So A, C, B, D, A, close loop. A, C, B, this is the path 1, B, D, A, the path 2. The total work done in moving the unit positive charge from A to B, that is via the path ACB, again B to A via the path BDA. That can be written as the sum of these two integral W1 plus W2. That is closed integral. The total work done can be written as closed integral E bar dot dr bar equal closed integral A to B. This is A to B, not B to S, sir. A to B E bar dot dr bar minus integral A to B E bar dot dr bar. So cancel, equal to 0. Therefore, the line integral of electrostatic field over a closed path equal to 0. So this is we got. Hence, the electrostatic field is a conservative field. Right. So the conclusion is, since the line integral of electrostatic field over a closed path, that is ACDBA, ACBDA equal to 0, electrostatic field can be say that it is an conservative field. Okay. Now, electrostatic field is an irrotational field. Okay, it is also one of the property of conservative field. Since it is a conservative field, the line integral of that electrostatic field over a closed path equal to 0. Already we proved now. So that is we have written closed integral E bar dot dr bar equal to 0. This is equation 1. But according to the Stokes theorem relates line integral and surface integral. According to the Stokes theorem, the line integral E bar dot dr bar equal to surface integral curl E bar. Okay. In vector analysis, first year, first semester, mechanics, you studied this one, very, very important. The closed integral E bar dot dr bar equals surface integral of curl E bar, del bar cross E bar. This is equation 2. From equation 1 and 2, you can write surface integral del bar cross E bar equal to 0. Okay. Therefore, del bar cross E bar equal to curl E bar equal to 0. So the curl of electric field equal to 0. The curl of electrostatic field equal to 0. The curl of electric field is 0 is nothing but there is no curl, no rotation. Hence, electrostatic field is called irrotational. Electrostatic field is called irrotational field. So this is the conclusion. Okay. So we discussed about what is conservative field, what is non-conservative field, right? So the line integral of electrostatic field. From that we approach, what is that? So we proved the electrostatic field is the conservative field. If it is the conservative field, the curl of that electrostatic field must be equal to 0. So that is also we proved here, sir. Okay. So this is about that one, right? Now, the next concept is this one. Electric field is equal to the negative potential gradient. It is also one of the characteristics. If any conservative field can be expressed as the gradient of some scalar potential. But in the case of electrostatic field, E bar equal to minus grad V, where V is the electric potential. Electric potential is the scalar. So E bar equal to minus grad V. So therefore, the statement is electric field is equal to the negative potential gradient. We have to prove this, sir. Yes. Consider this is in the electric field, you consider the two equipotential surfaces. On the surface at every point, the potential is V. On the second surface, the potential is V plus delta V. Here, the potential difference between these two surfaces is delta V or dV, sir. Now, a test charge Q0 is moving from point A to B. Okay. A test charge is moving by the field from point A to B. On the surface, on the equipotential surface, we will discuss in detail about this in the next class also. On the equipotential surface, the electric field strength is normally to the surface at that point. So here the direction of electric field strength is along this arrow line. So therefore, the force experienced by the Q naught will be Q naught E bar in this direction. Okay. So the force acting on the Q naught is the along this direction. Number one. Second point. Here the test charge Q naught is moved from point A to B, sir. Okay. Now let us approach. So same. This is all these concepts explained. In moving the test charge from point A to B, suppose that displacement is dl bar. Then the force experienced by the test charge Q naught, how much? Q naught into E bar. That is also explained. Therefore, the force applied by the external agent in moving the test charge from A to B. Okay. The force applied by the external agent in moving, in taking the test charge Q naught from A to B, that is F bar equal to minus Q naught E bar equal to minus Q naught E bar, equation 1, sir. Therefore, the work done by the external agent to move the test charge from A to B is given by d double equal to same F bar dot dl bar. Here F bar equal to minus Q naught E bar dot el bar, equation 2. From this you write dw by Q naught as the subject. Right side you will get minus E bar dot dl bar, equation 3. But dw by Q naught represents the potential difference between the two equipotential surface. We consider the two equipotential surface. So one surface is V, another surface V plus delta V. So then the potential difference between these two chord surfaces is dw by Q naught equal to dv, sir. Okay. Now, so let the coordinates of A and B are x, y, z, and B coordinates x plus dx, y plus dy, z plus dz respectively. Then the potential difference between A and B can be expressed as dv equal to minus E bar dot dl bar. This is equation 4, sir. That is equation 4. Okay, dv equal minus E bar dot dl bar. How we are writing? Electric field strength E equal to dv by length. So dv equal to minus E bar dot dl bar. Okay. Now, but dv equal to dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz. Because dv is the perfect differential, then this can be written as like this. Here v is the function of x, y, z. dv we can write like this, sir. This can be written as dou v by dou x I cap, dou v by dou y j cap, dou v by dou z k cap dot dxi plus dyj plus dzk. It is dyj plus dzk. Correction is a bar dot b bar formula. If you do the dot product, you will get this one, sir. So this is what it is, gradient of v, grad v dot. This is what it is, a dl bar displacement, small displacement dl bar, equation 5. In equation 4 and 5, by comparing equation 4 and 5, so there dv equal to, we have what, minus E bar dot dl bar, equation 4. Minus E bar dot dl bar. Here dv equal del v dot dl bar. Comparing these two equations, you will get E bar equal to minus grad v, that equal minus delta v. So this is the conclusion. Therefore, the electrostatic field can be expressed as the negative gradient of the potential. The negative gradient of potential or the negative potential gradient. Electric field equal to the negative potential gradient. Okay. In general, any vector field, any conservative field, A bar equal to grad phi. Here electrostatic field is the conservative field. Here we have the minus sign. E bar equal to minus grad V, where V is the electric potential. Electric potential is the scalar. So minus the negative gradient of electric potential gives the electric field strength. Okay. So this is about the conservative nature of electric field, right? Thank you. If you have any doubts, you can ask, sir. So నేను ఇప్పుడు మీకు లింక్ పెడతాను, స్టూడెంట్ అటెండెన్స్ ఫామ్ లింక్ పెడతాను. ఆర్ లిజనింగ్, సార్? అటెండెన్స్ ఫామ్ లింక్ పెడతాను. ఆ లింక్ మీరు దాని నుంచి అది అటెండెన్స్ ఫామ్ ఫిల్ చేయండి, సార్. అటెండెన్స్ ఫామ్, స్టూడెంట్ ఫీడ్బ్యాక్ ఫామ్ ఇప్పుడు నేను మీ దాంట్లో షేర్ చేస్తాను.